So we're in our series on the Black-Scholes model. I've talked about what is a derivative. I've talked about some basic knowledge we need, and now we're diving into the model. And I've told you that the Black-Scholes model is about modeling a derivative, and a derivative always depends on an underlying asset. And so we first need to think about how we model this underlying asset. And I will call ST to be the price of the underlying asset, and let's think about how this price actually develops over time. And let's try to think about a small time period. Let's call this small time period delta, and let's think about how this asset evolves over a small time interval. And since it is a risky asset, we would assume that this risky asset gives a return over the small time interval, and the first assumption is that this return is linear in time. So in other words, if I have an asset that gives 3% in 1 year, then it would give 6% in 2 years and 9% in 3 years. So it makes sense that we have return and it is scaled linearly by the length of the time interval. And in our case, the time interval is denoted by delta. So if I plot this model, then our asset would look like this. Our asset price grows linearly in time, and the slope of this is given by mu, the return. And if you look at this graph, this does not really look like a financial asset, does it? And the reason is that it does not move up and down randomly like financial assets tend to do. So we need to add something to our model, and what we add is Brownian motion. I've made a video on Brownian motion. You know that Brownian motion is this weird, very randomly up and down moving stochastic process. So what we could do is we could add a change in the Brownian motion to our model. And I've told you that Brownian motion is distributed with mean 0 and variance delta. And the variance is given by the length in the time interval. So you see that by adding this term, we do not change anything in the average return of the asset, we just add some variance. And since some assets have more variance than delta, we add a scaling parameter, sigma. And if we have an asset which has a variance of larger than delta, we just choose a sigma greater than 1. So how does this stochastic process look like? Well, it still has the same slope mu, but it has this random component, Brownian motion, to it, so that the stochastic process will evolve around mu, but it will have those random up and down movements. And this looks pretty good. I mean, this looks pretty much like a financial asset, doesn't it? And what we do with this model is we tailor it towards the specific financial asset. So if I have a financial asset which I want to model, I choose the mu and I choose the sigma so that our stochastic process resembles the financial asset. So now that we have the basic model down, let me introduce some notation. So what we do in math is we denote small changes with DST. So DST is a small change in the asset price. And this is dependent on, we said, mu, the return, scaled by the change in time. And this dt denotes a change in time, but d is always a small incremental change. Okay? And we also look at a small change in the Brownian motion times sigma. And this here is our central model we use for pricing an asset. So this is very nice. We have an equation for how our asset price changes, but what I would like is I would like to have an equation that does not depend on changes in variables, but on absolute values in variables. And that's what we're going to derive. And what I'm first going to do is I'm not going to look at a normal change in the price of the underlying, but I'm going to look at log changes. And this is just going to make our derivations later a bit easier. So I want to understand how the log of the asset price changes. And since the asset price is dependent on Brownian motion, we need to use Ito's lemma here. So what did I tell you? So if I have a change in the function dependent on a Brownian motion, what we have is we need the first derivative of the function times the change in the variable plus 1/2 times the second derivative of the function times a change in the variable squared. Okay? what is the first derivative of the logarithm? Well, if I want to have the first derivative of the logarithm, this is nothing else than 1 divided by x, right? And what is the second derivative of the logarithm? Well, the second derivative is nothing more than 1 divided by x squared, right? So let's use those two rules, but remember that our variable is not x, but our variable is st, right? The change in the asset price. So in other words, what we can write is the first derivative is 1 divided by st times the change in st, and the second derivative is minus 1 divided by st squared times the change in the variable squared. Okay? So let's simplify this a bit. So I have an equation here that gives me an equation for dst. So what I'll now do is I'll substitute our dst terms here. I'll substitute those two terms. So what do I get? I get 1 divided by st times the change in st, and the change in st is given by s small t times mu dt plus sigma dzt. So all I did was I used this equation and I rearranged it. So I got dst is given as st times mu dt plus sigma dzt, and I substituted this down here. Okay? And we can do the same thing with the second part. So we have minus a half, 1 divided by st squared times dst squared. So I'll substitute again, st mu dt plus sigma dzt, and then we need to square. Okay, let's look at this. So what do we have? We have that this st cancels, so we get mu dt plus sigma dzt minus 1/2. The st squared cancels as well, so we have the squared here, and we have the st squared here. Then I told you that d is a small change in time. So dt is a small change in time, and if we have small increments, then the dt squared terms are equal to 0, right? Because dt, so if the change in time is 0.01, then the change in the time squared is 0.0001, and this is almost 0. Yeah, this is a heuristic argument. This is not mathematically formal, but I will not go into the mathematical proof here. So dt squared is actually equal to 0, but let's use the binomial formula and try to expand this bracket. So what do we get? We get mu squared dt squared plus 2 mu dt dzt plus sigma squared dzt squared. And I've already told you that dt squared is equal to 0, so we can actually ignore it. And here's another rule from stochastic calculus: dt times dzt is 0 as well. This is just something you need to believe me. It can be made mathematically rigorous. It's just a long proof. And I told you that dzt squared is actually equal to dt. If you don't remember that, watch my last video. So what survives from this is, since this is 0 and this is 0, what survives from this minus a half sigma squared dt, right? And I further simplify by collecting the terms in dt. So what we get is mu minus a half sigma squared dt plus sigma dzt. And this is equal to the change in the log of st. Okay? So this was a very long derivation, and it's actually not that easy. So I invite you to look at it and to pause the video and to review every single thing I did. What we now do is we integrate. That's our second step, because remember our changes to get rid of those d's, of those changes in variables. So what I do is I integrate from small t to large t. So this is just a time interval, right? If you think on the time axis, I'm interested in how the price changes between st, which can be today, and large T, which might be the time that I'm interested in. Okay, so I integrate d log st. I integrate tt, mu minus a half sigma squared dt plus integral tt sigma dzt. So for the first integral, I get log at time t minus log at time small t, right? This is just the change in the log of st in the time period of the integral. For the second integral, I just get a change in time, and the change in time is equal to large T minus small t, and the terms before survive. And for the third integral, I just get a change in the Brownian motion. So I get sigma, and I actually forgot a square here. Sorry about that. Sigma squared zt minus z small t. Okay? And everything I need to do now is I can actually write this. Let me first write this differently. So log s large T minus log s small t can also be written as log s large T divided by s small t, right? This is just the rule in logs. And let me now take the exponential function. So if I take the exponential of this, then the log just goes away. So I get st divided by st. And here I just get the exponential. And all I do is I multiply now, so I take the st to the other side. And this is our final formula that we actually get. So if I am at a time today, right? So maybe my time today is t. Then I can actually calculate what my stochastic or I can use my stochastic process to calculate probabilities for what the price of the underlying asset will be at time large t, right? So what have we found? We have found a very elegant formula that kind of seems to match very closely how real financial assets behave, and we have calculated how in this formula the prices change of the underlying asset, and we also have found a formula for absolute values. So if you want to calculate the absolute value of a financial asset. And we're actually going to use this formula on a financial asset to derive the Black-Scholes pricing equation in the next video.